Okay, so hello everyone. This is an additional video to show you some exercise for curve sketching on chapter 4. So let me get started and try to sketch the curve. Okay, you can pause the video and then you can work on your own and then compare the results with me. Okay, so first we can start to check the domain, and I think the domain is it's all possible number of x, right? It's on all real number. And then check the intercept. Check the intercept. When x is 0, all becomes 0, right? And then check the when y is 0, then we will have x is equal 3. Or we can have x, and we can simplify, factorize this. So we will have x is equal 0 and x equal plus minus. Check. Okay, this will be 3 square root of 3. Okay. We can also check the symmetry. Check whether it's even or odd functions. We will have x this will be resulting that will be the result. So this will be negative f of x. So this will be odd function, which means there will be asymmetric on the origin. So symmetric about origin. So this means the graph is either like this or like this. So symmetric about this origin here. So remember the x cube is similar to this. It's also odd functions, right? Okay. All right. Now next thing we can write is there any asymptote? Okay, if you check the functions, let me write the function. I think there will be no possible asymptote, so you can check with limit. Okay, check with limit. I think it's still infinite, right? So no asymptote, no horizontal asymptote, and also vertical asymptote. There will be no vertical asymptote also, so no asymptote. Okay, no asymptote. Okay, next thing, we can check the first derivative and do some tests to see the functions, whether when will the function increase or decrease. Okay, the first derivative will be 1, and then for this 1/3, it will be minus x and then minus 2/3, right? Or we can write in terms of its reciprocal, and we can simplify, becomes that. Okay, we can check that, or we can see that when this is equal 0, our x should be 1, or x is 1. Okay. And also we can check the, oh, this should be plus minus 1, sorry, because it has x squared. Okay. And then checking the line number. And also I will put 0 here because 0 is x cannot be 0 from here, right? Okay. And then we can check the how the function increase decrease. So if we have 1/2 or half, or we have 2, what happened with 2 will be positive, right? It will be positive. And it will be decreasing here, I think decreasing, because if we have half, this will be negative and this is positive, so it should be negative, right? Positive. Oh, this should be positive, sorry. Should be positive, should be negative here. Yeah, between -1 and 1 it should be negative. -2, if we put here, this will be positive, right? Okay, so if we have this, okay, then it will be negative. This will be negative, and this will be positive, so it should be negative. So negative, so increasing, decreasing, increasing. So this will be our max, this will be our min. Okay, this is correct. Okay. And x equal -1 and x equal 1 will be our critical number. Okay, so increasing, if you want to make in precise and complete, we can write f increasing on and f is decreasing on this interval. Okay, I think this will be correct. And if it's asking the max value, so max value, you can check. Mean value, you can check. Okay, if you check the max value, plug in -1, -1 squared 1, it should be 2. -1, -3, +3 minus, okay, it should be 2 plus 1, and then check 1 will be -2. Okay, this is the first derivative test. Okay, next is the second derivative test. Let me write the f prime from the previous slides is so 1 minus x. Okay. And we can write the second derivative. It becomes 2/3. X is -1, so it should be -5/3. Okay, I think the one that is making x 0 is just 0, so it should be 0 is the probably inflection point. Okay, so you need to check this, and you can get this conclusion, and we can make sure that from our line number here. That is when we have the negative x, it will be concave downwards, and this will be concave upwards, or this will be negative and positive, right? Okay, so concavity, we can say concave upwards. On 0 to infinity, and concave downwards. This is from negative infinity to 0. I don't think this will be a complicated graph, so let's just try to graph here. Okay, remember that in the first derivative test we have negative 1, 1. Okay, so this will be positive, negative, positive. Okay, so we can start with the intercept. Okay, intercept, don't forget the intercept is plus minus 3, square root of 3, 0. So we will have let's say 1, 2, 3. Okay, negative 3 here, and maybe this will be the intercept is here. 2, 3. So 1 and 3, and maybe here is the intercept. And start with this will be positive, negative, and then positive again. Okay, so we can start to graph from this point here. Okay, graph, and then this will be the max. We have max is here, this is 2, this is negative 2. We can make the point first, okay, to help us draw. Okay, probably like that, and then we need to cross the 0, 0 to get the inflection point. So this will be making the concave downwards like that, concave downwards, right? This will be the maximum point, the negative 1, 2. This will be also 1, 2. Let me draw first. And then going down like that, and going up. Okay, I hope it is clearly to see the maximum and minimum. So this will be the max and min. So max, min, this will be the inflection point. This will be 0. Okay. Yeah, I think, and then this will be the intercept. Okay, I think we done. Okay, let me try another functions. Okay, let's try another one. Let me give you the trigonometry functions. Okay, let's say we have the functions is 2x negative tangent x. All right, we can check. Okay, you can try first, and maybe let me give you the domain we are going to have. Okay, so of course this will be our domain. Okay, and then we can start writing the intercept when x is 0. So all will be 0, so 0, 0. Okay, and then when the f of x is 0, then 2x is equal tangent x. You can write in the calculator, and you will get the x is 0 or x is plus minus 1 1 7. Yeah, okay, doesn't mind this. Okay, this will be just some x, okay, that will be crossing, so the curve will crossing some axes. Okay, so try it. You can use calculator if you want to make sure, because if you use the radian, you are not, maybe sometimes you're not sure on how many decimals it will be in the graph. You can check with calculator if you want. Okay, and if we have the minus x put inside, it will be minus 2x plus tangent x, right? Because tangent, if it's in negative, it will be negative. So this will be the negative of the original function. So f is odd function, right? So it's symmetric, but it's symmetric on the origin. Okay. Okay, finding the asymptote, I think based on tangent, you know that there will be an asymptote, right? Okay, so we can have a limit. We can check the domain. First is the negative pi over 2. We can check the from the right. Will be positive, okay, and we can check pi over 2 from the left, because we only have the domain from negative pi over 2 until pi over 2, so we are only considering this part here. Okay, so from the limit from this will be negative. Okay, so from this 2, this will be our vertical asymptote, and then there will be no horizontal asymptote. Okay, and then the f from x will be 2 minus secant squared x. Okay, okay, if we are going to check the critical number, we can check the critical number is when secant squared x is equal to, so secant x is square root of 2, or this will be 1 over cos. So this x will be pi over 4, and we have plus minus. We can check when it will be increasing, decreasing, maximum, minimum, but I think we can check with the line number. Can check with the line number, and we can also make this with the asymptote here. We can include, okay, checking the secant. You can try some pi here, and you will see that it will be decreasing here, right? And it's increasing, and then decreasing one more. So negative, positive, negative. Okay. So this will be half max on the positive. This will be resulting this, and minimum, this is negative pi over 2 minus 1, plus 1, sorry. Okay, next is the second derivative test. We can check the second derivative. Let me try the write one more time the first derivative. Okay, Okay, the second derivative will be negative 2 secant x and then secant x tangent x, or this will be negative 2 tangent x secant squared x. Okay, we can rewrite this form. If you remember, the sine squared x plus cos squared x equal 1. Okay, divide all with 1 cos squared x. So this will be tangent squared x plus 1 is equal secant squared x. So I can change the secant squared with tangent. So I can write this equation with the tangent squared x plus 1. Okay, now from here we can equal this equation with 0. Okay, and we'll see that tangent x is 0, so x is 0, and tangent squared x is equal negative 1. And I don't think this is okay, so because it's having squared and then it's negative 1. Okay, so we are considering this 0 here, that is in our line number. Di sana dulu deh. Dikit lagi, Bapak, satu lagi. Okay, now we can check the terms that is negative and positive. Okay, so maybe we can check with pi over 3 or pi over 6. Okay, we can check with this negative and then check with pi over 3, pi over 6. Okay, pi over 3 tangent 60 is 1, so we will have a positive, and it will be a negative, so this will be negative. Okay, this will be positive, right? Okay, now we can move on to draw at least how it looks like. Okay, we can draw this and make it maybe pi is here, pi over 2 here. Okay, so this will be pi so pi over 2, or let me write maybe in terms of the equation here and equation here. Okay, now remember that the first derivative test resulting with it's having this 2 pi over 4 pi over 4 pi over 2. So this will be negative, positive, right, and then negative. Okay, so maybe here's the pi over 4. This will be negative pi over 4. This will be pi over 4. So this will be having the mean and max right there. So this will be having mean. Okay, so it's going down and then going up. Okay, max value, or this is mean value. Mean value will be negative pi over 2 plus 1. This will be pi over 2 plus 1. So maybe about here, or maybe here. Okay, so this will be the mean point. So let me draw for you guys. Okay, so let me change the color. Okay, there we go, and then it will going up until 0. Okay, this will be the inflection point. Okay, I forgot to mention this was the inflection point. Okay, this will be the max. So you need to show that this will change its concavity. And then crossing down like that. Okay, I think we get it. Okay, this will be the maximum, minimum. So maximum, minimum, and inflection point here. And you already get all the necessary numbers. Okay. Okay. But I think we get it. And yeah, that's it. Okay, let me go through another okay, we can start with another trigonometric, because I think I haven't told you in details for the trigonometry in class. Okay, now what we can do from here, we are having a trigonometric function but in a rational form. So for checking the domain, you notice that it has this 1 plus cosine x. So we are going to exclude in the domain that is x should not be equal with 2n plus 1 with pi, where n is integer. Okay, we can also write this form in terms of rationalizations. Okay, so we can multiply with this. So this will be equal with sine x, 1 cos x, and this will be 1 minus cosine squared x. So it will be, this will be sine x, and this will be another form that we can write. We can check the intercept. Okay, we can check the intercept when x is 0. It's also 0. When the y is 0, we get that sine x is equal with 1 plus cos x, and that is x equal to n pi, and n is integer. Okay, every time I write n, it should be meaning the integer, like in the trigonometric equations. Okay, we can check the symmetry. This is actually precisely going back to the original equation. If you look at the sine and cosine, so it will going back to sine x, 1 plus cos x, because cos is the same when you have the negative part, right? So it will be the same as this. Okay, so it will be an odd function. That means it's symmetric on the origin, but it has a period. Okay, so okay, maybe this is some my short explanation on the trigonometric, because if you see if you have sine x, you will have a period. Okay, you will see maybe from 0 to 2 pi, you will see like this, one period. But eventually, every 2 pi, it will have the same graph, and then you can continue that to the to every 2 pi. So every 2 pi, this will be the period. Okay. Now if we see the odd function here, we can say that its symmetry about the origin, okay, and every period, okay, every period. This period is 2 pi, okay. Okay, now we are going to check another possibility if there is any asymptote. Okay, if we check limit, if we have sine x over 1 plus cos x, we will have some certain line that will not cross. It's depend on this bottom equation here, right? That's mean if we have some pi or some n pi, okay, as x approaching n pi, where n is odd integer, okay, in this case, let's say from the left of our functions, it will be resulting on infinite number. And if we see from the other side, from the right, okay, if we check the n with some odd integer 3 4 3 5 7, okay, you will see that it is going to approach negative infinity. So of course this n pi or x equal n pi is our vertical asymptote, okay, and I don't think we will have the horizontal asymptote, so no horizontal asymptote. Okay, that's the first section here. Okay, next is we need to check the critical number, decreasing, increasing, and concavity. Let's start with, let me write one more time the function. Okay, I will just going through the quotient rule directly. Okay, so this will be cosine x, 1 plus cosine x, okay, and then minus sine x, and then this will be minus sine x, and this will be let me check, cos x plus cos squared x, this is plus sine squared x. Okay, now the top one will be 1 plus cosine x, the bottom one will be 1 plus cos x squared. So I can take this in terms of 1 over 1 plus cosine x. Okay, if we look here, notice that cos x, it can't be negative because it will be making a 0, right? If we have negative 1, so we can pretty sure that the f prime x, or the first derivative, is always positive. Okay, so you can check probably in between of negative 3 pi and negative pi, and then pi, and then 3 pi here. So this will be the asymptote, 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 asymptote. We can check every possible x, okay, for the cosine, because cosine, if you have cosine negative pi over 2, it's 0. So probably here will be the the cross point, so this will be having going up, this is also going up, so always positive. Okay, the slope always positive. Okay, and then if we check the second derivative, we can check the one, we can check from this first derivative. Let's say this is -1, so we can write this and because the bottom here is positive functions, then sine x, if we want to find the inflection point when sine x is 0, so x should be 0, right? So 0 will be an inflection point. And also it's depend on also -2 pi, and every 2 pi period, right? So 4 pi, -4 pi, also 6, 8, that will be the inflection point. So from here, we can also check the concavity first before we move on. So check from 0. Okay, let's just checking this this period here, period from -pi to pi here. Okay, so we are checking this. Okay, checking the inflection point. X equals 0 is inflection point. So check the maybe pi over 2 or -pi/2. So if you check pi/2, this will be resulting positive, okay, which means it's concave upwards, and this will be negative, and it will be downwards. So if we draw this sine or the sine over 1 plus cos x, so let me write the original function. This is the functions, and let me draw maybe here. Okay, probably there, and then take the this -pi, or let me maybe just write the or make the line first, okay, to make up the asymptote. Okay, okay, I think a little bit here should be oh sorry, it's also here. Okay, I think that will be better. Okay, and then we can start to write. Okay, this is the x -pi x pi, this is x equal 3 pi, this is x equal -3 pi. So this is 0, this is -2 pi, this is positive 2 pi. Okay, so here we go. It should be having a positive slope. Let me draw positive slope like that. This is also having positive slope, and this also having a similar notions. Okay, and then we can draw the graph. So from -pi to 0, it should be concave downwards. So it should be having a little bit like this. Okay, and then going up like that. It should be having the same way here, and should be a little bit identical graph. It's also the same. Okay, and that will be our solution for this trigonometric functions. Okay, Okay, I think we can go for a little bit more. I think I can give you one more question and then we can wrap up this recording. Okay, let's say we have a functions of 1 over x plus ln x. Okay, let me give you an example of ln. Now starting with the domain. Okay, you can check first. You pause the video, check first, work out on your own, and compare the results. Okay, let's start. So domain, x here should not be equal 0, and also x here should not be 0, right? And this also need to be positive, right? At least it should be 1, so that will be ln 1 is 0. So domain will be 0 to infinite, okay? From this functions here. So because x is not equal to 0, there will be no intercept, and then if f of x is 0, this is not possible, right? This is not possible. Because if x is 1, there will be 1 plus 0 still having 1, right? And then we don't have any intercept. Okay, so no intercept at all. Okay. Next thing, we check this. And this is not a symmetry. Okay, this is not the same as this. Okay, so this is not the same. Okay, so no symmetry. Okay, now because we are of course having exception on the domain on 0, we will probably have the vertical asymptote. Okay, so let's check from the right, because that's the domain of fx. This will be resulting it will be having an infinite. Okay, so x equals 0 will be our vertical asymptote. Okay, so check the first derivative. 1 over x become negative 1 over x squared. ln x become 1 over x. Okay, or we can write this in terms of x minus 1. Okay, now we can check this, and probably the x can be equal 1 for a critical point or critical number, and there will be an asymptote here and on x0. So we can check from maybe half. This is clearly negative. I think this is easy to be observed, right? Because the number calculation, it's all not too complicated, right? So this is positive here. So we'll have a minimum point at x equal 1. We can check when f1, this will be 1, ln 1, this will be 1, right? Okay, the other thing we can check is the concavity. We can check this will be positive 2 over x cubed and minus 1 over x squared. And again, we can have this 2 minus x. Yeah, 2 minus x. Okay, so 2 will be probably the inflection point. So if we have 1, this will be positive. If we have 3, it's negative, right? If we have more than 2, it will be a negative. So it will be concave upwards and then concave downwards. Okay, now I think I can make it all this smaller, and then we can draw on the same page. So this is 0. Let's say this is 1. This is 1. 1, 1 is our minimum point. And then we will have decreasing on 0 to 1. So f decreasing. Let me write here. And increase. Concave upwards. And concave downwards. Okay, so how it looks like, it will be, so this will be going down like that. Okay, probably like that. And then let me write this 2. And f2 is a 2 plus ln2. Or 1 over 2, sorry. ln2 is around 0.6. This is 0.5, so it's around 1 point something, so maybe around here. So it will be going like that, and then change the concavity. It should be really like small change like that. Okay, so it should be showing that this is upwards like this until 2, and then downwards. Okay, and that will be our graph. Okay, okay, I think we can stop here. And oh, by the way, for the trigonometric here, if you see any, like, if the graph has periods, okay, you can focus first on how it looks like on the maybe the very basic here. First, you check here, okay, so you don't need to worry about so if it has, like, for example, making this 2n plus 1 blah blah blah, okay, so you can be relaxed. Okay, you look for maybe the one that is, so if you look at the cos x here, okay, let me check here. If you look at the cos x here, okay, so of course cos x could not have to be equal a -1, so there will be some x that makes the functions negative, right? So that you need to put an exceptions for taking this this asymptote here. Okay, so probably you will find that you will have -pi and pi, okay, because sine or cosine, okay, cosine -90 is the same as cosine 90. Okay, remember cosine has that property. It has the fourth quadrant on the trigonometry. If you remember trigonometry, that is the cosine property. Okay, but for example, for sine, if you have sine -90, this will be negative sine 90. Okay, got it? Okay, I hope you get it correct. So you check the x, and x will be -pi and pi. Okay, you can start with these two first. You can start with these two. Start with these two. Okay, and then you got this drawing, and then because the period of the trigonometric, okay, it's having period on 2 pi, so every 2 pi, so this will be 2 pi. This is also 2 pi here, and 2 pi backwards here, and you make the same graph, and then that's how you make it actually. Okay, so if you maybe confused on the integer, on how to find the integer, maybe sometimes you are nervous on the exam, you can do like a simple thing like this, and then at the end you can make the general formula for some n, and n is the integer. Okay, that's how you can draw the trigonometry. Okay, I hope this can help you. I will give you, and you can check the exercise also. I give you exercise. It's not an assignment, it's just as exercise to help you to see what kind of question we have, okay, in this curve sketching. And of course I will not give you something that is really complicated in the exam, because I need to check at least you understand first on how to sketch a curve based on calculus. Okay, so see you later in class.